Hi everyone. As we were discussing in the last episode, we today experience a certain understanding of the space we are in, of the time we are living, and beyond, owing to the meditators of truth. There have been many such to say so, yet not a very common occurrence in the course of history. So, today's episode is dedicated to the life and work of whom I personally am a fan. uh, I love reading his essays, articles, and the many insights he had to offer in the domain of mathematics, logic, philosophy, religion, education, politics, almost every field. Um, of the many exciting mathematical stories he was a part of, here is one of them. Um, After this, if any one of you can recall what you know of his life, we can discuss that. And I will not tell the name of this mathematician. I'll tell the story and then you can guess who that person is. So the story begins with a question whose solution led to the development of a completely new mathematical field. So I'll present the question to you all so that we can appreciate the solution which he gave. And I'll turn it over to the experts here so that they can explain us the question and then we'll see what was the historical development behind it. Um, I'll just share my screen. Can you see my screen?
Yeah, we can see it.
Yeah. So this is the question. You all can read it and maybe uh, give your insights on what can be the solution, or maybe we can first discuss what the question actually means. What are we looking for?
Let's see. Mm, Okay, is this an exact quote or is it a paraphrase? I feel like it's an exact quote.
It's an exact quote.
Yeah. This seems more like the two-body problem or the three-body problem. Is it?
Yes, yeah.
Okay. Then I won't guess any further. I'll let others, yeah, think about it and guess the person. Yeah, anyone has an idea?
So this question was a part of a competition proposed by King Oscar II of Sweden.
Mhm.
He proposed four questions in collaboration with a mathematician of Sweden. Uh, one, so this is the first question, and the prize was given based on the solution of this question.
Mhm. I see, I
So
see.
this is one part of it. Uh, so this was the context which was given when the question was presented.
I see.
I
Um,
hope the font is fine.
yeah, it's fine, it's fine. I guess for the viewers, maybe one of us can read it out. I can read it out.
Yeah.
It seems that this problem, the solution of which will considerably enlarge our knowledge with regard to the system of the universe, might be solved by means of the analytical resources at our present disposition. This may at least be fairly supposed because shortly before his death, Leon Dirichlet communicated to a friend of his, a mathematician, that he had discovered a method of integrating the differential equations of mechanics, and that he had succeeded by applying this method in demonstrating the stability of our planetary system in an absolutely strict manner. Unfortunately, we know nothing about this method except that the starting point for its discovery seems to have been the theory of infinitely small collisions. It may, however, be supposed almost with certainty that this method was not based on long and complicated calculations, but on the development of a simple fundamental idea, which one may reasonably hope to find again by means of earnest and persevering study. I see. I see. Actually, mm, what I know of this problem is slightly, I had a different idea, but this seems to say that there is a different idea without spoiling too much of it. So I'm very curious what this is. Yeah.
Yeah, can anyone else guess what exactly the problem is? So, as Rahul said, it is an n-body problem, not just two bodies, but n-body problems
Right, right,
in a dynamical system with certain conditions.
right. So yeah, people can take a stab at it, I guess.
Yeah, so we can think about it. Till then, I'll just continue with the story.
Yeah.
Uh, yeah, so as I was saying, in the summer of 1885, King Oscar II of Sweden, he, in collaboration with Mittag Leffler, announced a mathematical competition. And he told that he'll give 3 years uh, for the questions to be solved. And on his 60th birthday, he'll announce the winner. So it was, it is a three-body problem in celestial mechanics. And as said, Dirichlet said that he claimed that he solved the problem, but then there was no solution to be found. He told his friend that, yeah, I had solved it, but there is no written record, so we don't know about it. Um, so 12 entries came in of the solution. Of them, five were of the first problem. And so when the solutions were reviewed, only three were of some real importance. The so out of the three, it was very difficult to select which one will be correct. And the one which was selected, uh, so the committee was sure that yes, this is the right answer and everything, and it was selected. And the condition was when the solution will be presented, it will be printed in journal Acta Mathematica. Uh, So so that's when the main difficulty arose. When they were going to print the whole paper of uh, research paper, the problem was the mathematician who wrote the research paper, he was so direct in his way of writing that the committee themselves didn't understand exactly what the solution is. Uh, the insights were far beyond their time. They knew it somewhere that it is right, but they didn't understand it completely. Um,
Did they know the person by name beforehand, or was it basically anonymous?
yeah, they knew the person. I'm not telling his name, but they knew the person.
They knew the person.
So
Yeah. Okay.
yeah, they knew the person. So they approached him again and they asked him to explain certain arguments which he had written. And when he was so the mathematician, when he reviewed his own paper, he found certain errors in them.
Mhm.
Uh, so when he found the errors, he realized that they were not small errors, but it they a substantial change was required.
Mhm.
So he, within 20, 21 days, changed all of it. again gave it back to them, and still the committee didn't understand. But uh, uh, because the person who presented it was so clear on his part, and he was a renowned mathematician, the paper was printed, and then it was only in 1960, after I think some 80, 90 years later, that that the paper was uh, actually the value of the paper was actually recognized, and
Mhm.
a new domain of study in mathematics opened up. And that study and that a field of study is chaos theory.
Right. Wonderful. Mm.
And the that field is still not very uh, uh, being worked upon yet. So
Yeah.
basically, that mathematician, even after 111 years, uh, the uh, uh, the question he solved is still under uh, uh,
Yeah.
evaluation.
We can
So the
maybe, yeah, we can maybe briefly explain what these three body problems are, because or the n body problem is, because I guess the wording there is
yeah,
pretty old, so it might not be
yes.
really clear. So who wants to go ahead? Or do people know the n body problem here? Uh,
I've
uh,
heard of it, but I don't really know what it is. I assumed it's three bodies moving in some forces like gravity, obviously, and you can't really calculate all of their positions at once or something like that. I don't know.
yeah, yeah,
Like from what I know, it's not entirely deterministic. It's all like there is no confirmation. You can't be aware of exactly where either of those bodies will be in X seconds into the future.
yeah. All very good answers. Yeah, that's
The last
basically it. Yeah,
the
go on,
last thing
Arjun.
I had heard about the three body problem was that it was the answers range, as in like if you try predicting the model, it's just that the calculation exceeds your computing power,
Mm.
but that
Yeah,
might be a mixture of the third differential problem as well.
yeah. So all very good answers, and they get at certain aspects of the three body or the n body problem in large. So essentially, there is some sort of a central force, and the context in which this has been stated is gravity. And when you have just two bodies gravitating towards each other, around each other, your solution is perfectly deterministic. But as soon as you have the third body come in, um,
Mm.
it is proved that there is no analytical solution. So it's just not just that we haven't found the solution. You cannot have a solution, and that's why these as soon as you have just one more body enter in, one more particle, you can only have numerical solutions that are approximate to a very high degree, but they're still approximate. And it's so weird that even in case of go for it, Arjun. Yeah,
So I was just asking, when you say it's analytically proven impossible,
Mm.
is it
proven to
such
be
that
analytically impossible. Yeah,
it is analytically impossible?
yeah,
Uh, is there a solution such that it follows chaos theory where you can where you can to a certain good amount of degree predict the path of the
yeah.
whatever
So
system if you know the initial conditions? Is it similar to that, or is it that even if you know the initial conditions you still can't find the path
even if you know the initial conditions, you don't have a closed form solution to the path
at all?
at all. Yeah, you can only get at numerical approximations. But it's so interesting to think about this. Like, oh, we go into string theory, quantum field theory, and things like that. But this is a very basic problem where you have gravitating bodies, just three of them, and we cannot have a closed form solution that talks to how limited our understanding is of our universe by design, which is very interesting. And forget about n bodies, like our solar system, which has more than at least 9 bodies, if you include comets, etc. But yeah, so it's very interesting. But anyway, coming back to, so that's the problem essentially. And the reason is, we can go more into it in one of our future episodes. But
Yes.
so for actually, I'll let Muskan take over again. I won't give the analysis of the proof yet. Yeah.
Yeah, so do you know who the mathematician is?
I know at this point, but I want others to.
Is it the founder of chaos theory or is it somebody else?
It's somebody else.
Okay.
Well, actually, you could call him the founder of chaos theory, but yeah.
I mean, the
Yeah,
founder of
his
chaos theory is
paper,
Lorentz, right?
Uh, that's a good guess, actually, with Lorentz attractors, but not really. No.
Mm.
So this guy, he was called the first universalist, first and last. Maybe, I don't know if he's the
the
last
last
universalist.
universalist.
The
So
last
after him,
universalist.
we didn't
Yeah,
get another.
yeah. And Abhiram,
He was
you,
born in
Oh,
France.
yeah,
Um,
France. Yeah.
Like the universalism movement is what
No,
we're
no,
talking
no.
about here?
Universalist in terms of math and physics and so on.
Hmm.
uh,
he has worked a lot upon automorphic functions as well. If
Yeah.
anyone is reading them.
Yeah, Abhiram, you've definitely heard of his name and have worked on
ah,
his results. We've in fact discussed this.
His
Yeah,
not
I mean,
only his research papers on math, but his philosophical essays are also very famous,
yes.
which is frequently shared in our group, I think.
Yeah,
Uh,
and he's French.
he's French, yes.
yeah.
He's before the Bourbaki.
Hmm.
Oh, okay. Uh,
He has studied in the famous French institution, École Polytechnique.
is it Poincar?
Yes,
Yeah.
it's Henri
Yes.
Oh,
Poincaré. Yeah.
yeah.
Henri Poincaré. I don't know if all of you have heard of him, but
I have heard of his name. I've not
yeah,
heard of his works, but I've definitely heard of his name.
well,
Yeah,
now
same. I'm
you've
just
heard of
aware of
his
his
work.
existence.
Yeah, yeah. Now you've heard of his work as well. Yeah.
Hmm. So he was the creator of the, like, I mean, at least of the idea of the three body problem, or one of the solution givers.
So yeah, the problem was stated by, as Muskan said, King Oscar, was it?
Yes, with Mittag Leffler, so the mathematician Mittag Leffler, and the
Mhm.
committee who was reviewing the papers included Carl Weierstrass and Charles Hermite as well.
Oh, from the Hermite polynomials.
Yes,
If you study quantum mechanics, you'll come across these polynomials. They describe the quantum harmonic oscillator. Yeah.
yeah. Uh, so this was the committee, and the person who was reviewing the paper of Poincare was Lars Edward Fragment, and he had a hard time editing his paper when it was being printed in the journal because Poincare had this quality that although he had a lot of clarity in his mind, but he's known to be very impatient to write everything each step. He worked on his intuitions and he did not support the idea that mathematics uh, uh, is born purely from logic. There is a large part of intuition in that too. So he has a lot of essays on that as well, arguing that intuition has a greater part than logic in the whole study of mathematics.
Fusionalism.
Yep, yep.
Yeah.
Yeah, and there's actually it's a very deep problem, this of intuition, right? Um, it's something that's so intangible, and people usually put it off to like, oh, like intuition is just combination of or compilation of more logic, and it's just a higher order or something of that. But it's actually much more than that. Where I don't know if you've heard the phenomenon of emergence, where the whole is greater than the sum of the parts. So it's like it cannot be reduced to just a sequence of logic, but a phase transition happens, a new order is developed, and that is intuition. Yeah, just give me a second. Yeah. So yeah, it's something to think about. And I guess Poincare's reflections, is it, is a
Yes.
very nice article to go through. It's on the CFRC website as well. But yeah, it's very nice. But yeah, thanks for the story, Muskan. Yeah.
Yeah. So, if everybody agrees, I wanted to discuss like,
Mhm.
so this story has certain aspects to it. So I wanted to put this question forward, that how do we describe this incident? That uh, isn't it commendable that the way people involved managed the whole crisis which happened before the paper was published and the knowledge was shared? So, and what can we learn from this incident? Because Poincar would have just not cared to correct everything and go through it everything
Right.
again, or maybe the committee, they didn't understand the paper completely, so they would have rejected the paper, but they still considered it. So
Yeah,
we can
it
maybe
is.
discuss on those lines.
Yeah, it is very curious, right? How the committee decided that this proof was actually right,
Hmm.
even
I
though they
mean,
didn't completely understand it. Yeah, go ahead.
yeah, like that's why I think they went back to Poincar, right? Like to ask him himself, like, what have you written here?
Right,
So,
right.
I
There
mean,
might always be the reason that the other papers that they had received were even worse,
Even worse. And this was, yeah,
and this
the
was the
other
most
papers.
acceptable condition.
Yeah, probably the other papers they understood and knew it was wrong, and this they didn't understand. So there was the benefit of doubt. Yeah, maybe.
well,
Exactly.
also, I mean, it is people who are like genuinely interested in into logic and mathematics and things like that. You know, when you see something that you completely don't understand, you're immediately sort of attracted to it. You got to know what it is. So
Yeah.
that all because the committee itself consisted of very
Mathematician.
Yes.
mathematicians and all such guys. So I feel like they would, even if it wasn't even like, even if they weren't in the editorial committee, they just read in the newspaper or something, they would definitely have tried to contact Poincar and maybe
Right,
ask
right.
what this is and things like that.
Right. Yeah. There's also this thing about how differently one can approach mathematics. So we spoke about how Poincaré is very intuitional.
Hmm.
Um, so he was known to be one of the fastest minds in mathematics. Like that's where the intuition, everything comes in. But there's actually another person who who's known to be one of the slowest minds in mathematics, but is of the same stature as Poincaré. Yeah, and yeah, the amount of well, the contribution of his to math is comparable, if not, you can argue, exceeds Poincaré's as well. Um, uh, Let me give some hints here. So this mathematician um, sat through one of Einstein's lectures. So obviously he came later, and he actually solved general relativity before Einstein could.
Is it not? Is it Lawrence?
No, it was
No.
not Lorentz. Yeah, Lorentz, Einstein used Lorentz special relativity math,
yeah.
essentially. But yeah, and he solved it, but nevertheless, he let Einstein take the credit, of course, for general relativity. Curiously enough, his name comes up a lot in quantum mechanics as well. So general relativity and quantum mechanics, but he
It's
himself
fine.
is not a physicist.
Is it
Yeah.
Dirac?
No. Dirac was a physicist, but
He was.
yeah, but obviously he was a mathematical genius, nevertheless. Yeah, so that's also there. Let me give more clues. If I give this one clue, maybe it's a giveaway, so I'll reserve it for the last. Let's see what else I can give. He actually, if I'm not wrong, I may be wrong about this, went to school with Minkowski from the Minkowski spacetime. So Arjun, Minkowski spacetime is the four-dimensional spacetime where, you know about it.
The
light
complex
cone.
space-time.
Right, exactly. Since you're going to complex analysis, I thought this would be good.
We
So
just
yeah,
discussed in the last section, last session.
right, exactly. Oh, you did, right.
Not exactly Minkowski's, but in general, how space-time and how four-dimension
Work, exactly. So, and he was German. He started the German school of math, I would say. I hope I'm not getting that wrong. Yeah. Any
German.
guesses? Okay, I guess I'll give this clue. He also proposed a list of problems that mathematicians should solve in the 20th century.
Hilbert?
Yes,
Hilbert?
it was David Hilbert.
Hilbert.
So that's why when you so there is this thing called the action for every theory, and if you see general relativity, it also has an action. It's called the Einstein-Hilbert action. And in quantum mechanics, you deal with the Hilbert space, which is a space where your wave function exists, essentially. And Hilbert went to school with Minkowski. Yeah, I'm not aware if they had personal interactions. That would be a fun thing to find out. But yeah, back then it was called a gymnasium, I think, the school. At least the Germans called it that. So yeah, so he's funnily called the slowest mind in math. He himself calls himself that. Yeah. But that is also because of the way he went about things. He was never considered to be the brightest in the class or whatever, but he took his time. He slowly thought about things. And yet he made those significant contributions. So the point is, there are these different flavors to math and different approaches to it. And one needs to really actually think about these things. And yeah, it can give a lot of insight as to how there are different ways to approach things. And there isn't really a set way to approach math like schools teach us. Yeah. Okay, I guess that's a great place to end this episode. Awesome, guys. It's really nice. It was really nice to think about these things. I guess we'll meet the next time. Yeah. All right. Take care. See you.